Hi everyone. Recently I was asked to look at WACE 2014 question 17c. As a rectangular coil loop UVXY is moved from left to right, it enters a uniform magnetic field B as shown in the diagram. The plane of the loop is perpendicular to the magnetic field lines. According to Faraday's law, an EMF must be induced in the loop. Assume that the EMF induced in the UVXY direction is negative, while in the YXVU direction, the EMF is positive. What does this mean? If an EMF is induced that causes current to flow in the closed loop direction UVXY, then that EMF is to be considered negative. While the opposite EMF that causes the current to flow YXVU is to be considered positive. Now, before we go further with the question, it's important that we try to imagine what is happening. We have a uniform magnetic field B and a coil that is passing from left through the middle and then out through the right of that magnetic field. Part C of the question asks us to draw a graph of the voltage being induced across the loop for the duration of its journey. We are to map out the voltage as the loop enters into the field. We're to map out the voltage as the loop passes through the middle of the field. And then we are to map out the voltage as the loop leaves the magnetic field. The question reminds us that the velocity is constant. Looking at the graph as shown here, we can see that it is different to the sinusoidal voltage graph we see when we look at a rotating coil type generator. The lines in this graph are constant values, not curves, and can be seen to take three different parts: negative in the beginning, nothing or no voltage in the middle, and then positive at the end. This video is intended to show how this graph can be predicted. As we focus on the question, we must break the journey of the coil into three parts. First, there is the coil entering the field. Then the coil is moving through the field. Then finally, there is the coil leaving the field. Entering the field, the coil starts with no flux passing through it. As it enters into the field, flux passes up through the coil. This change in flux experienced by the coil induces an EMF according to Faraday's law. If the coil were a closed loop, we would see a current flowing through the coil. Lenz's law tells us that the current would be in a direction that would oppose the change in flux being experienced. The current would have to flow UVXY. This would create an opposing field down through the coil to counter the increasing field up. Because of the rectangular shape of the coil and because of the orientation of the coil to the field and because of the constant speed of the coil into the field, the voltage induced in the coil would be calculated by VBL. The voltage induced would be constant because the speed of the coil, the length of side XY, and the field strength B would all be constant. The voltage would remain constant until the coil was completely immersed in the field. Once completely in the field, there would no longer be a changing flux through the coil, and so there would no longer be an EMF. Another way to think of this is that once the coil was completely in the field, the EMF induced by the side XY would be cancelled out by the EMF induced by the side UV. When the coil finally leaves the magnetic field, it experiences another change in flux. It goes from having maximum flux up through the coil to having no flux at all. This change again sees an EMF induced across the coil. Faraday. The resulting EMF is in an orientation to oppose the change being experienced. Lens. This time, the EMF tries to send current in the direction YXVU. If this were possible, this would result in a bolstering of the flux that is being withdrawn from the coil. On our graph, this would be a positive EMF. Again, it would be constant for the same reasons as before. Constant speed, constant side length. This time, it's the tailing side UV that's doing the EMF. And constant field strength B. So as we finish the question, we can see that there is a negative EMF generated as the coil enters the field. There is no EMF generated as the coil moves through the field. And then there is a positive EMF generated as the coil leaves the field. I hope this was useful.